In this video, we are going to continue talking about the concepts of Chapter 12. We are now going to learn how to classify alcohols. When it comes to the classification of alcohols, as we can observe in the upper right side of the slide, alcohols can be classified based on the number of carbon chains that are connected to the carbon that is holding the OH. The classifications of alcohols are primary alcohols, which it can be denoted by this number 1 in that little circle. In a primary alcohol is where your carbon with the OH is connected to one carbon chain. A secondary alcohol, which can be shown by this 2 in that little knot circle that we have on the right side of the digit, are shown or are classified based on the carbon atom that is holding the OH. It is connected to 2 carbon chains. Lastly, alcohols can be classified as tertiary because the carbon atom that is holding the OH is connected to 1, 2, 3 carbon chains. As practice, let's look over some of these examples and classify them as primary, secondary, or tertiary. When you're classifying alcohols, it is important to write in the carbons and the hydrogens that are in the molecule itself. So we can observe for the molecule on the left, this is cyclohexanol. The carbon that is holding the OH is here. I'm going to write in the carbons within the cyclic system. The carbon that is holding the OH is a CH group, while the rest of the carbons are CH2s to complete their octets. So when I inspect cyclohexanol, I can observe that the carbon that has the OH is connected to 1 carbon chain, 2 carbon chains. So cyclohexanol is an example of a secondary alcohol. Let's look at the next molecule. In the next molecule, let me write in the carbons and hydrogens. This is a CH2, this is a CH, this is a CH3, CH, CH2, CH3. The carbon that is holding the OH is connected to 2 hydrogens and the rest of the molecule, which means that there's only 1 carbon chain with all those carbons right here connected to the carbon that is holding the OH. So this alcohol specifically is a primary alcohol. If I label the molecules as A and B, determine the classification for the molecule A. If you determine that this is a secondary alcohol, you are correct. Now determine the classification of molecule B. If you determine that that is known as a tertiary alcohol, you are correct. The next functional group that we're going to talk about is thiols. Thiols are characterized by organic compounds that have a carbon chain connected to an SH group. Oxygen and sulfur are atoms that are within the same group in the periodic table, meaning group 6. Now, even though these 2 elements are in the same group, we see very distinct properties comparing thiols and alcohols. It is known that thiols specifically, for some reason, when we detect their smell, they have very strong and not so pleasant odors. So, for example, in nature, it is known that skunk spray has a mixture of thiols. And you can imagine how the smell of skunk spray is not pleasant. Other smells that some people may not like include the smell of cheese and oysters. And as you can see, this is the thiol responsible for them. The smell of onions. We also have a thiol responsible for its smell. And even garlic has a thiol specifically that is responsible for its smell. The important thing about thiols is to recognize them structurally. Next, we're going to talk about solubility of these functional groups when it comes to water. Alcohols, ethers, and thiols, as long as they have a small number of carbon atoms in their structure, they will be soluble in water. Now, when it comes to alcohols, because alcohols contain that OH group, when we see alcohols interacting with water, they do it via hydrogen bonding to the water molecule. So we can observe that in these structures, which are just given by just molecular models, our water molecule, the red dot is an oxygen, the white dot is going to be hydrogen. So let me just include them. We can observe that alcohols can actually perform a number of hydrogen bonding events with water. Furthermore, in the textbook, you can actually see what is the trend for solubility of alcohols in water. Alcohols of 3 carbons or less, they're very soluble in water. For example, 1-butanol is slightly soluble in water, and 1-pentanol, just to summarize the concepts of chapter 12, table 12.1, 1-pentanol is actually not soluble in water. So keep in mind, 3 carbons or less, very soluble in water for the alcohols. When it comes to ethers, because they contain an electronegative oxygen atom, ethers also of 3 or less carbon atoms can form hydrogen bonds with water, and it allows them to be soluble. The minute that you increase the number of carbons in an ether to more than 3, then the solubility is diminished. When it comes to thiols, understand that they have a similar trend to alcohols, but thiols tend to be less soluble in water when it comes to alcohols. So in general, we think of thiols of having 2 carbons or less being soluble in water, but in general, most thiols are just slightly soluble or insoluble in water. Now, specifically, we also learned that a benzene ring can be attached to a hydroxy group, and that is known as a phenol. When it comes to phenols, it is interesting that even though those molecules have 6 carbons in their structure, because of the benzene ring, remember that it has 1, 2, 3, 4, 5, 6. Phenols will be the only molecule that has more than 3 carbons, but it actually happens to be soluble in water. The reason why phenols are able to be soluble in water is because they actually undergo an acid-base reaction with water. And we can see that acid-base reaction in the bottom of the slide. When a phenol molecule is placed in water, we can observe that the phenol molecule is going to lose a hydrogen. That means that in this reaction, the phenol molecule is suggesting that this molecule is acidic because we see the loss of the proton. In turn, we see that water is acting as a base because it accepts the proton from some phenol. In turn, when phenol loses its protons, it makes a conjugate base that is called the phenoxide ion. And in turn, since water accepted the proton, it forms the conjugate acid hydronium ion.